And why, in conclusion, I'm going to tell you why we should forget about water saturation and think bulk volume of water for reservoir modeling. So to remind you, why do we need a reservoir model? Well, nobody goes down there, so we have to invent a model of the reservoir so we know where to place the wells, also how to calculate the hydrocarbon in place, and is used for simulation. This is a model here. It's like a Lego model of different colors, and the different colors could represent different zones or different fascies types or different porosities. It's a model. The model requires us to understand where the fluid contacts are, the net reservoir cutoff, and most importantly, we need an SW versus I function, which I'll tell you in a minute. Now, to describe this model, we've got very limited data. We've only got the data from the well locations. From these well locations, we've got electrical log data, the logs, and we've got a limited amount of core data if we're lucky. So from this limited amount of data, we've got to get a very solid model. We need to know where the hydrocarbons are in this model. So it is used to initialize the 3D reservoir model, this function. It tells us how water saturation varies as a function of height above the free water level. In your model, you've got hydrocarbon throughout. You've got water throughout. In every cell of your model, you've got water and hydrocarbon above the free water level. And you need to know the proportion of water saturation of different fluids in your model. The function also tells us the shape of the transition zone, which is very important. Now, a good saturation height function requires 3 independent sources of data to be consistent. These are your formation pressure data, like from the MDT or RFT, electrical log data, your gamma rays, your densities and resistivity logs, and very importantly, your core data, your core water saturations, core porosities. The function requires us to be able to cope with varying permeability and contacts throughout the model. It's very difficult to map permeabilities in your reservoir model, so you need a function which can deal with that. So once you've got a model, you need to upscale it from the log values every 6 inches or every 2 feet to the size of the cells. So it must upscale correctly, and I'll explain how that is done. It should be convincing and it should be easy to apply. So this is the result, and then we'll go into how we get this function. The function is called the BVW function, the FOIL function, or the fractal function. But basically, it is saying that the bulk volume of water is a function of the height above the free water level. The bulk volume of water is the porosity times the water saturation. And this function is independent of fascies type, porosity, and permeability, as I'll explain. So 2 parameters, A and B, completely describe your reservoir. I'll go into that in a little bit more detail. So let me show you the first case study of where we apply this to understand where we're going. This is a data set which was supplied to the London Petrophysicist Society a number of years ago. It's a very difficult data set. It's a very heterogeneous formation from the North Sea. As you can see, the porosity varies tremendously, and especially permeability. You've got very high permeabilities and very low permeabilities, and it's quite a shaly formation, as shown in green. Now, the water saturation, as derived from the resistivity log, is shown in this column here. And those who've seen water saturation before, generally the water saturation decreases with the height above the free water level. But in this case, the water saturation in this real well actually increases. So it was very difficult to provide a function. So this client in London was very crafty and asked all the petrophysicists to have a shootout to see if they could derive a function for this very difficult data set, very heterogeneous formation, especially how SW increases with height. So to do this comparison, we're using the resistivity log as being correct, and we can see which function can give the best match to this, whether it's a Leverett J function or the Skelton function, or in this case, the BVW function. And this is shown on the next slide. So the BVW function is just a simple function of height, and is shown in red. The resistivity derived water saturations via the Arch equation is shown in black. And the comparison is shown here between the red from the function and the resistivity. And there's a very good match, especially there's a very good match as in different lithophase types, even in the high permeabilities and in the low permeabilities, is a very good match. So therefore, we do not need permeability as an input to get this function, even though water saturation is a function of permeability. It is defined by only two parameters, A and B. So if we can calculate water saturation with this accuracy, do we need resistivity logs? Now, what I mean by that is that if we derive this function from the best wells in your field, in the later well, perhaps the resistivity log fails in the development well, would you go to the expense of another day's rig time to reacquire the resistivity log if you could derive your water saturations from the other wells as accurately as this? Now, let's return to the definitions we'll be using here. We need to agree upon these, as you see on the screen there. I'm going to go through these 4 definitions quickly. So it is key to understand what we mean by BVW, the bulk volume of water. It's simply the porosity versus water saturation, the product of the two, and represents the percentage of water in a unit volume of rock, where water saturation is a percentage of water in the porosity in the rock. It's a percentage of a percentage. And you remember from school mathematics, percentages of percentages do weird things. So we're trying to move away from water saturation. So it's what we measure, BVW. We measure BVW by the electrical logs and by core analysis. Logs and core do never measure water saturation directly. They always measure, the logs measure the conductivity of the porosity, of the conductivity of the water. And in core analysis, we measure the bulk volume of water, the amount of water dispelled from the core under different pressures. So BVW is more fundamental than water saturation. Obviously, you get water saturation by dividing BVW by the porosity. Now, the free water level is very important. The free water level is where fluids will separate out in a very wide borehole, as shown here. It is also, as you know, is the intersection of pressures. The free water level from the aquifer, the water leg, and the hydrocarbon leg. Notice that these lines are straight, and they indicate the free water level. So this is a formation pressure information. We need it to know the free water level as the basis for our SWI function. And this is shown here for very high porosities. In contrast to that, well, let's go back. So the free water level is an horizontal surface of zero capillary pressure, whereas the hydrocarbon water contact is a height where the pore entry pressure is sufficient to allow hydrocarbon to start invading the formation pores. So therefore, it depends upon the local porosity and permeability. And this will be a variable height, not a plane, it'll be variable. And some fields, it is so variable, some clients think they've got multiple contacts when they first look at it. Now, the irreducible water saturation. Your reservoir engineer will ask you for the irreducible water saturation. The irreducible water saturation does not exist. It is defined as the lowest water saturation that can be achieved in a core plug. And it's achieved by flowing hydrocarbon through the sample or spinning it in a centrifuge to get lower and lower water saturation. So therefore, SWIR, the irreducible, depends on the drive pressure or on the centrifuge speed. So therefore, it will continue to decrease more you spin it. In the reservoir, SW will decrease further you are from the free water level. So it depends upon the height above the free water level. So a minimum does not exist. If the reservoir engineer asks for one, the best you can do is to give them the water saturation at the highest or the shallowest log depth. It extends indefinitely from the free water level to the top of the reservoir. I will later explain. And the BBW is a function of height and porosity. Let me show you this real case study. This is from the southern North Sea, and it's a gas field. And it shows a very typical pattern. We have water saturation between 0 and 100% against the height above the free water level, in this case in feet. Now we're using a z-axis of color. So for very high porosities, in this case above 16 porosity units, are shown in red. And these are Aeolian sandstone parts of the reservoir. And as you expect, the water saturations are quite low, and it's got this asymptotic loop to it. Now, as we move to the blue, which is the fluvial sandstones, the data then moves up and to the right. And when we move to the sandy Sabkha, which is a lower porosities, less than 12 porosity units, the data has moved well to the right and well up. So it's a typical shotgun pattern. The low porosity formation is shown here is fully water saturated for hundreds of feet above the free water level. Now we need to put lines through that so we can model it for the reservoir modeler to describe it in our reservoir model. And these are the actual lines that were submitted to the government agency to develop the field development plan. So you've got water saturation against height, and they found that it was best to define SW by different porosity bands, as shown here, the very high porosities to the left and the low ones. So not only do you need to know where the lines are, but you need to know where the ends of the lines are, where the hydrocarbon has actually entered the formation. So these porosity bands in this actual case study are not very convincing. Why? Because they actually cross each other, but they're derived from the data itself. But not only that, you need to drill wells in poor parts of the field so you can define the pore entry pressure. And this can be very difficult. So this was a challenge for SWI functions. So let's look at our data again. We're plotting only the net reservoir data and define net later. We've got this pattern. The eye can see that there are trends by porosity. Now we're going to change this plot so the x-axis, water saturation, changes to bulk volume of water, BVW. It's going to show you exactly the same number of points. And this is the result. So we've got BVW. Remind you, this is the percentage of water in unit volume of rock. This is what core and logs actually measure. Now what happens? The shotgun pattern collapses to almost a straight, a curved line like this. And this trend is independent of porosity because the porosity, the z-axis, is now intermittent. Some people say, well, you've still got a bit of a spread there, but the spread is due to the different vertical resolution between the porosity logs, which is 2 feet, and the resistivity logs, which may be 20 feet. And I'll explain more about that later. So the point is that the porosities are intermingled. We don't need to have SPWLA functions by porosity. This is the BVW. So the BVW is independent of rock properties. Now, how can we prove that? Well, you prove it by using a very powerful petrophysical tool, which is called the cross plot. So you plot your SW against height, and then you change it to BVW, which only takes a few seconds. So this could be your level J data. You've got SW against capillary pressure. You change it to BVW, and if it all condenses to one line, then it is independent of that. So you can prove it's independent of facies, different permeabilities, and porosity. Now let me tell you about water. Water is very important in understanding SPWLA equations. Now, as you know, H2O consists of two molecules, two atoms of hydrogen and an atom of oxygen. But you may not realize they're in this boomerang pattern here. So it's polarized with a distinctive negative side and a positive side. So this causes the different molecules to be strongly attracted to each other and also to the reservoir rock. In actual fact, this force is 10 to the 36 times greater than the gravitational force. So we shouldn't ignore it. Now, let's consider our reservoir. Water is in the reservoir first. Then hydrocarbons migrate into the trap, gas or oil. And the buoyancy force exerted by the lighter oil or gas pushes the water down that was previously there. Now all the water cannot be displaced because some of the water is held by those strong capillary forces that I mentioned there. Now, narrow capillaries, pores with smaller pore throats, with larger surface area, hold onto the water the strongest. Now, you've probably seen this. Where two fluids meet in a capillary tube, there is a difference between the pressure at the interface. The capillary pressure is caused by preferential wetting of the capillary waters by the water and gives rise to this familiar pattern. But you probably didn't realize that you also get this pattern on the outside as well. And this is and it's even greater there because the surface area is greater. And you've probably seen this as well, and that the smaller capillaries hold onto the most water and actually draw up the water more strongly than the large capillaries. So consequently, hydrocarbon requires more pressure to enter the small pores. And it is all described by the mathematics, and I won't go into this, but it is the capillary pressure is a function of these parameters here. Now, what is important in our case is that the capillary forces are holding up the water. Opposite to that is the gravity pulling the water down. And this is simply determined by the difference between the water and oil densities by this equation here. So the water at a given height in the reservoir is determined by the balance between the capillary forces holding up the immobile water and the force of gravity pulling the water down. The oil or gas is the mobile phase and only is allowed to enter the leftover space that the water doesn't want. They're there first, and they're claiming it with that strong capillary force. So throughout the reservoir, the pore space contains both oil and water everywhere. And we know that the split between oil and water, the percentage split, is called the water saturation. Now, the capillary bound water comprises of a continuous column of water within the oil leg, as shown here, and also throughout the water, through the aquifer as well. And it continues as a straight line. The oil is located in the remaining pore space, but is also a continuous phase, as shown as a dark line on the right. So we've got two pressures there, the oil pressure and the water pressure. Even though they coexist, the pressures on these two fluids are different. The intersection of the oil gradient with the water gradient is a free water level. Now, the formation pressure tester only sees the mobile phase. This is important. Even though there are two phases here, the water is immobile, capillary bound, the oil is mobile, and that is what is seen by the pressure tester. Now, the buoyancy pressure, the difference between the oil and water phases, increases with height. So this difference increases with height. Now, as the buoyancy pressure increases, the oil phase can displace the water from the increasingly smaller pores. So therefore, generally speaking, water saturation tends to decrease with the height of the free water level. But as I showed you before, this is not always the case. Now, I want to tell you about fractals, because these are very useful in reservoir modeling. You've probably seen diagrams like this. We see fractals everywhere. We see them on the small scale. When it snows where you are, you'll see these different snowflakes. There are fractals. It's a repeating pattern. You see it in different vegetables, like the Roman cauliflower shown here. That's a small scale. You even see fractals on the big scale. This is a photograph from the International Space Station of the Himalaya. You can see that the major ridges are these shapes, but as you go in closer, the smaller ridges are the same kind of shapes. And as you get closer and closer, it's a simple repeating pattern. Similarly with river channels. I took this photograph when I flew from Qatar to Iraq a couple of years ago to give this presentation. And as I flew over the delta there, I could see these river channels. And the river channels are the same however close you get to it. So we see them on the big scale. But we also see fractals on the really big scale. And how can it get any bigger than the cosmic microwave background? I took this from a page in Professor Brian Cox's book. And this is what you see is a cosmic microwave background. It's the leftover signature from the Big Bang. Now, what's important here is that when you zoom in on these patterns, the patterns repeat. So from the big pattern, we get these galactic superclusters. And as we zoom in on those, we get galaxies. The universe is fractal all the way down. It repeats itself. And this is very useful for reservoir modeling. So a fractal is a never-ending pattern. It's infinitely complex and it looks the same on every scale. And it is created by a simple repeating process. Other names for fractals are self-similarity or scale invariance. So let me give you an example of fractals as you see here. Looking at a tree, as you look at the tree from a distance, you see the main trunk and the main branches. But as you're moving closer, you see that the branches are the same shape as the overall tree. And the smaller branches are the same and all the way down to the twigs themselves. And there is a reason in nature I could go into why it is that way. So fractals are a mathematically simple way of describing complexity. And where do we see complexity? In reservoir models. So fractals, I'll show you, are very useful. But how can you prove something is fractal? Let me show you this example of the Great Britain's coastline. If you wanted to measure that, you just need a ruler. So with a ruler, you can measure the coastline, but the coastline's length, n, depends upon the length of your ruler, r. So as you use smaller and smaller rulers, you can get into the estuaries and into the little basins and rivers, and you can continue this all the way down to pebbles on the beaches. And what you notice is that the coastline will get longer and longer, smaller and smaller the ruler. So what can we do with that? Well, we plot the length of the ruler against the coastline measured on log scales. So shown here are 4 coastlines in different colors, and there they are on this plot. And what you notice is that they're in a straight line on a log scale. The fractal dimension is the gradient of that line. So that is how you can prove something is fractal, is by just plotting on a log scale. So where does this come into reservoir modeling? Well, we need to know the porosity of the rock. Now, the porosity can be derived by one simple technique with a scanning electron microscope. We take a slice of the rock, we color the rock with some kind of dye, and then we just get the computer to count the number of, say, blue spots which relate to the porosity compared to the overall rock shape. So you realize as you're getting closer and closer, you're going to see smaller and smaller pores, and therefore the porosity is going to increase. But it does level out. If you plot the pixel size, the size of the pores you're looking for, against the porosity you determine, you get a straight line. And this has been done for dozens of reservoirs. This is a Brer sandstone from the North Sea, and you see that we've got a very straight line. Even though you've got this massive complexity in the rock, this porosity here is much different than there, but overall it's fractal. And we can use that to our advantage. I won't go into much detail with the mathematics because they're in the paper, but all the fractal formulas is said the pore space is related simply to the radius of the rock capillaries. And you can manipulate this equation to derive the BVW function. And this is the reference for the paper. Right, net cutoff, another definition we need to understand. This is required for when we're upscaling the reservoir model parameters. It is defined as a portion of reservoir rock that is capable of storing hydrocarbon and is therefore relatively easy to pick, usually based on a porosity cutoff. Now, this, in contrast, we have net pay, which is much more complex, and that is the proportion of reservoir rock that can produce commercial quantities of hydrocarbon, and is useful maybe to select perfect intervals, but it's very difficult to pick. All the hydrocarbon in your reservoir is potentially producible, but you need to drill lots of wells. You'd have to have a good gas flood and a water flood. It would be very expensive. So net pay depends upon the oil price. So forget about net pay. For our reservoir model, we need net reservoir based on a porosity cutoff. Now, what does our BVW function tell us about net reservoir? It says BVW is a function only of the height above the free water level. What do we mean by that? Take this depth in your reservoir, say it's 100 meters above your free water level. On the left, your reservoir here, we've got good porosity rock, 20 porosity units. On the right, we've got poor reservoir rock, say 10 porosity units. These are the same height for the free water level. Now, the water was there first and claimed what the pore space based on capillary forces. So this is the amount of water in the good quality rock, and therefore it gives us a water saturation of 40%. Whereas in the poor quality rock, the BVW is the same and SW is 80%. So in this case, the net reservoir cutoff is 9 porosity units. Let me show you that again. Net reservoir is defined as a rock capable of holding hydrocarbon. It is very important for averaging porosity, permeability, and water saturations for the reservoir model, but it does vary as a function of the height above the free water level. It varies as a function of the height. Let me show you that. Let me show you this case here. We've got a reservoir with varying porosity. We've got the core in dots, and we've got a continuous porosity there. In this reservoir, we've got a much varying shaliness and porosity, but one thing doesn't vary very much, and that is that BVW increases slowly as we go down. At this height, well above the free water level, we've got low saturations of capillary bound water, and the hydrocarbon enters the smaller pores. This is net reservoir. Whereas just above the free water level, which has got a similar porosities, and it contains high saturations of capillary bound water, and there is no leftover room available for hydrocarbons, and therefore this is non-net reservoir. So the BVW function is easy to calculate. BVW is a function of height and just two constants. It's an exponential function, and as you remember from your school mathematics, this is a straight line on log scales. So if you take log of both sides here, you get a linear equation. Now this can be shown if you plot your data. This is core data. BVW against capillary pressure. The BVW function is a function of just two parameters, the intercept and the gradient. The gradient is B and the intercept is A. But what you notice here is that in all these different fields of very different geological age and different depositional environments, all these lines are straight. This proves that the BVW function is this simple function. In actual fact, these fields suggest that we could have calculated the BVW function from just 2 points. It only takes 2 points to define a function, a straight line in log space. So a lot of these very expensive measurements were not necessary. Yeah. What also you notice is, even though they're straight lines, they have got a similar gradient. Now this gradient is scale invariant. You can change capillary pressure to height. You can change height from meters to feet. You get the same gradient. And you notice that the gradient is the same. So perhaps all the fields in the world are defined by the BVW function with the same B. And B in this case is 0.42. The answer was 42. Now, how can we believe this BVW function? We need to have a test to whether it is correct or not. So let's compare the BVW function, as shown in red, with the resistivity shown in black, and the core, which is shown as these blue dots. This is a thin-bedded reservoir here. We've got high-quality core data, Dean and Stark. The well has been drilled with oil-based mud, doped to identify any contamination. And we take the samples from the center. So we're confident that the core water saturations represent the real situation. Now, the BVW function matches these points, proving that is correct. Now, whereas the resistivity log is off to the left. Why is this? It's because the resistivity log can be affected by conductive shales up to 20, 30 feet away. So it's very poor identifying resistivity and hence water saturation in thin beds. So this is why we believe BVW function, because we compare it with quality core data. So the BVW function doesn't only give us one reservoir model, it gives us two, right? We've got the model, which is the BVW function is shown in purple here. And this represents the initial oil in place. The resistivity derived water saturation by the Arch equation perhaps is shown in black. And this represents the current oil in place because you took the logs yesterday. So you're comparing yesterday with millions of years ago. So you can use this to have a differential reservoir model. The resistivity log is shown in track 2, where the BVW function is shown in the right-hand track. So by comparing the two, it gives you a wealth of useful information. So this top zone here, we have a difference. It gives us the residual oil saturation, but it also tells us that this interval has been swept. Whereas a deeper zone here, the function and the resistivity SWs overlay. So therefore, this indicates a zone which has got bypassed hydrocarbon. So you need to use reservoir model here to find out where you can chase oil in your reservoir. The resistivity log can be incorrect in thin beds, close to bed boundaries, and where there are conductive shales. The BVW function ignores thin beds, bed boundaries, and shales, and is therefore useful. The BVW function can be used to pick the free water level. This is another case study from the North Sea. 2 wells don't intercept the free water level. We want to use the data to be able to predict it. The BVW function ignores porosity and the variability in permeability. So therefore, it gives you a simple line. So you overlay the 2 wells, and then you predict where the free water level is. And this is a real example as shown here. Clearly, you need to speak to the rest of the team to confirm that both wells are actually in the same compartment and have got the same fluids. Now, I said the free water level is the most important for the reservoir model, but the hydrocarbon to water contact is also useful. And you can get that very simply by dividing BVW by porosity to get water saturation. And your simple line will then drop out with different porosity bands. So why is this useful? Because it gives you the height in parts of reservoir where the reservoir is fully saturated with water. In this case, when you've got 5 porosity units, part of the field, the reservoir is fully water saturated up to 200 feet. So this is consistent, and it's all you derive this just by dividing your BVW by porosity. Now, BVW has been used for depth control. Depth is probably the most important petrophysical measurement. If your porosity is out by 1 porosity unit, that doesn't matter too much. But if your depth is out by 1%, that could be hundreds of feet. So it is very important. Now, the depth can be out by plus or minus 30 feet due to survey errors and also depth measurement errors. So we've used this function to normalize the depth between different wells if they're in the same compartment. So this is a recent case study. We found that the free water levels were out by several feet between the wells. we believe the wells were in the same compartment and recalibrated these depths to the satisfaction of the experts. And the field's equity moved between the two companies by 3%, which is significant for $1 billion field. So my last case study I want to show you is that this is bringing together many years of looking at different fields. And we brought together here many different fields which are very different. These fields contain gas, oil, condensate from different depositional environments, deltic, fluvial, and a massive range of porosity and permeability. On the left, we've got the standard poroperm plot, showing that these wells are, as expected, the average permeability and the average porosity follow this trend. So what information can we gather from looking at these very different fields? So let's compare what we call the transition zone. As I say, extends from the free water level to all the way to the top of the reservoir. Now, if you wanted to find a great field, what would you want to see in that field? Well, you want to see lots of porosity, because this is where the hydrocarbon is held. You want to have great permeability, because that is a conduit to getting the hydrocarbon out of the reservoir. But also, you would like to see a transition zone, which is off to the left here. So these colors represent the colors on the previous slide. So the transition zones are very different for these wells. And what we'd like to see is one over to the left in the ideal field. So for a certain height above the free water level and certain porosity, we've got the lowest water saturation. Now, the shape of this transition zone is related to pore geometry rather than porosity and permeability alone, which I explain later in the paper. And this pore geometry is quantified by the BVW function. Now, let us just compare the logs with the core. As we said, the BVW function is linear on log-log scales. So we've got BVW against height for the logs, and this represents the data from the free water level all the way top to the reservoir. On the right here, we've got the core data. We've obviously got more core plugs, and we've got capillary pressure, which is the same as height. So those are the core-derived BV functions and the log-derived functions. Now, what we notice that they are the same irrespective of whether they're from logs or core. And this is what we expect because it's fractal. This represents small rocks, this represents the old reservoir, it is the same function. Now, this is an advantage because we can quality control the core against the logs. If these functions are not the same, we need to look at our data again. Perhaps the core plugs are fractured. Maybe the logs have not been filtered for bed boundary effects. They quality control each other. Now we want to upscale the water saturations for our reservoir model from 6 inches to the size of your cells. It's very important. We need to average permeability, porosity. Porosity is very easy to do. You just add up the porosities in the cell and divide by the number, and that's your average. Now, petrophysicists know it is a little bit more complicated when you use water saturation. When you take an average water saturation, you have to multiply it by the porosity. It's pore bound weighted. You have to pore bound weight the water saturation before you find the average. Now, what do you notice? Porosity is water saturation with pore volume weighted, BVW. So we're actually, to upscale, it is best if we use BVW. And Paul Worthington, who is an expert in SPWLA function, says that any function which predicts a BVW is especially appropriate to give you good averaging. Also, the function gives you uncertainty. You'd like to give to the client, the operator, the oil company, some idea of uncertainty in results. So you don't just give them your average function, which is your P50, but you also give them an upside and downside. And this This can be done by calculating the P10 and P90 functions, where it includes uncertainty in porosity, resistivity, and all your parameters. So this gives you three functions. You put those into your model, so it gives you your average oil in place in your model, but it also gives you an upside and a downside. Very important. So in conclusion, the BVW function is derived from the fractal nature of reservoir rocks. It can be derived from log data and core data, preferably both. And on log-log scales, it's just a simple line. You only need 2 points to define a line. Or if you believe that B is 42, you only need 1 point. So as they give the same function, they QC each other. And when you send off a small core plug to a core laboratory, and it comes back with a leverage J function, the client will say, well, how can that small core plug represent all of my reservoir? You've got a leverage J function from a core plug, but I want it for the whole reservoir. I said, well, it's the same because it's fractal. The function for the core plug is the same as for the whole reservoir. The function gives you the net reservoir cutoff, the shape of the transition zone, determines the free water level, and the hydrocarbon to water cutoff. Nice thing about it is independent of rock characteristics, your zone, your fascist type, your porosity and permeability. So you can forget about thin beds, bed boundary effects, and shaleyness. And it can be therefore, it's a very simple implementation in your reservoir model. Now the key conclusion is, forget about water saturation, think bulk volume of water, because that's what we measure. Thank you. I'm happy to answer questions today and afterwards by direct email or through LinkedIn.
Thanks very much, Steve. Great presentation. And we can see by the number of participants, we have 55 people joining us, which is in one of our highest ones, that's for sure anyway. So we have a couple of questions. I'll start off just actually, Ryan, if you can ask your question first, you can unmute yourself and ask directly.
Hi, Steve. Ryan Lafferty, Petrophysicist at North Oil Company. I'm just wondering if you can go back a couple of slides where you showed the bulk volume water cost plots comparing log and core.
Which ones? This one?
You had a no, probably 3 or 4 more back. Yes.
That one? No. This one?
With the core and log BVW.
That one. We've got the core on the right here with the BVW against capillary pressure, which is the same as height from the logs.
So just my question relates to the uncertainty. So where you showed the saturation profiles for your P90 to P10 range.
Yeah.
Are you able to, I mean, you know, we see quite a degree of scatter in these BVW plots, obviously with a similar gradient, but different intersects. Could you take this set of data and define your uncertainty range in BVW terms and then correspondingly SW from this range in scatter of the data?
By comparing all the different fields against each other. Yeah.
Hang on, sorry. Oh, this is different fields, isn't it? Okay. Sorry.
This plot here shows you that even in a single field, we've got 6 shown here that which are very different, right? But they're all on a straight line. So these core plugs are representing very different porosities and permeabilities for that field, but they all fall on a straight line. So the BVW is indicated from the core data alone that there is no change. But I did say earlier on that there is still a residual scatter in your data here. There's still a residual scatter. And people say, well, you've got some uncertainty there. Well, that residual scatter is due to the depth resolution, because you need to create these points by knowing the porosity, which is 2 foot vertical resolution, combined with resistivity, which may be 20 feet. So that is residual. What I'm trying to say there, that there is no way you can use porosity to improve your function, as we're doing with the porosity banding with SW. And you can use the Z-axis for anything you want, permeability, fascies type, or whatever. If you could get a separation, then you could have 2 functions for different fascies. But we have consistently shown that this BBW is independent of rock type. You don't need a geologist.
Yeah, okay, thanks. I misinterpreted that previous cost plot you were showing me. I didn't realize it was for a number of different fields. Sorry. Okay, thank you.
Thanks, Steve. Thanks, Ryan. Sanjeev, your question, I think, comes next. If you can unmute yourself and ask it. Thanks. Sanjeev, are you there?
You could read it out if you wish.
Yeah, I will. So really what he's asking is for reservoir modeling to capture the heterogeneity. It keeps on disappearing as more questions come up. To capture the heterogeneity, they group it into different rock types, having different fluid properties. Yes, there you go, Sanjeev.
Hello.
Ask directly.
Yeah. See, hi, Steve. Very nice presentation. Thank you for that. I have a very basic questions. You have shown that for a different stratigraphic zones of different age as well. So BBW is capturing well the relationship between the water situation and the capillary pressure. Now, if we talk about a specific reservoir, we have a lot of features in it. It means I have a porosity range starting from the 10 to 30, and to capture it very correctly for the simulation part, so that the fluid properties also go along with that. So, do you think that BBW will honor that, or what we do the FZI based classes and then the water situation based on that? So that will honor more than this concept.
You talk about the variability of the BBW for a particular field. Yeah.
Yeah, but for a particular reservoir, that's also we have a lot of phases variation, right? So how to capture that in BBW?
You got different
one straight
phases.
line for the total field, right?
It's independent of the fascies type. It's all controlled by the capillary pressures. The water is the most important here. The water is held there by that massive capillary forces, and then the hydrocarbon can only enter what the water saturations don't want. So it's a very simple function of due to the capillary pressures, and the fascies types are secondary. Perhaps you could have a plot where you've got different functions by different fascies, but how would you put that in a reservoir model? You'd have to map your fascies throughout your reservoir model first, and then apply a slightly different function depending on the fascies at that point in your reservoir. So I would use a simple function unless you can move away from that in a particular field.
Okay, but if I have already did facies types in my model, say 3 or 4, so I can define independently for these 3 different BBW functions?
Yes, of course. You could have a different function for each fascies type, and then the reservoir modeler could very easily calculate it at that point in the reservoir model. But what I have to do first is to plot water saturation against height, and then change the BBW, but your Z-axis would be your fascies. Now, does the fascies information give you more information? Maybe it would separate out, and therefore you could have a different function for different fascies, which is very unlikely. But if you did, then you just use a different BBW function for the different fascies in your model. Yes, you could do that.
Okay, thank you.
Thanks, Steve. I think we'll go now to Ronak, please.
Yeah, hi, Steve. It was a very nice presentation. Thank you. Thanks for that. I have a question that whatever we are seeing right now is on considering that it will be water wet reservoirs. But if we have an oil wet reservoir, will this function work accurately in that condition as well?
This model is brilliant for oil wet. Why is it why is that? If a reservoir is oil wet, it was never initially oil wet. It's only oil wet subsequently for different charging and flowing of hydrocarbons through the reservoir. Originally, the field was water wet. Right, we agree on that. Now, the BBW function gives you the water wet function. Now, the resistivity log will give you the data from yesterday. Now, this is after all this recycling of hydrocarbons to the reservoir, and it is lost being 100% water wet, and it's partly oil wet. Now, by comparing the two, resistivity log SW yesterday by the BBW function, it can tell you where in your reservoir it is water wet, and also quantify how water wet it is. So it is we've used it in fields which are known to be oil wet, because actually, remember, this function is actually telling you what it originally was. So we need to compare it with something.
Thanks, Steve.
Okay.
And I think linked to that very maybe two short ones is from Faisal Sural, which he's saying, if the reservoir contains both oil and gas, where does the height above free water level for gas interval start? Should it start at the gas oil contact or start at the free water level? When
you've got oil and gas, I've got a separate presentation on that, and it's very important. You've got two free water levels. You've got the free water level to water, and you've got the free water level to gas. Now, the free water level to gas is actually in the oil leg itself. Now, it's not a serious problem, because you can calculate the free water level by the intersection of your oil to your water, but you can calculate your free water gas contact by just the intersection of your water leg with the gas. What is important to realize then the reservoir modeler has to be given two different BBW functions or SWI functions, and both are tied to a different depth. The oil is tied to the free water level. The gas is tied to the gas water level, which is actually the oil leg, but you only apply it to the levels of the reservoir which are actually gas.
There we go, very clear. Thank you, Steve. Maybe a last small one, and then we'll pass over to one of the more complicated ones that's here. So quick one, very interesting from William Bottomley. We always talk SW, which is a percentage of a percentage. I'm wondering if oil saturation plots nicely against any parameter if we use BV oil instead of BV water.
Yes, there are a number of SWI equations which are based on BV oil, and I recommend that to use a volume in either case, because these are measured by the different tools, and you measure the volume of oil or the volume of water or whatever. You don't measure this percentage of percentage. So I recommend that whether you use the BBW function or you can use a BB oil function, you could find that. So I can send some links. The oil function also works very well, but I think the BBW is more important because the water is telling the story of what the reservoir was like shortly after charging, and that's the valuable story. But BB oil is also very important, but definitely move away from water saturation.
Thanks, Steve. And then we'll go to Joe Millward, if you'd like to unmute yourself. And then the last question will be Jan Lutgart. So over to you, Joe Millward, if you unmute yourself.
Yeah, thank you. Hopefully you can hear me. Yeah, thank you very much for that talk, Steve. So my question is, using this function within the reservoir model, you then have to divide it back by porosity to derive water saturation. And if you were in a gas field like you were showing in the southern North Sea, and you're very tight at the top of the reservoir, and you divide it back by porosity, wouldn't you just get back, high water saturation at the top of the model? And then thus, when you try and simulate it, you've got an issue.
Yes, the net rock can be 100% water saturated, as I there. Yes, in the cases here, in this, can you see the plot? Yeah. So right at the top of the reservoir, this is actually reservoir up here, but it's 100% water saturated, and that is purely because the net porosity cutoff has dropped below a certain value, say 10%. We've still got porosity there, but it is full of water. Similarly, in the middle here, we've got some tight stringers, and the porosity has just dropped below a cutoff, and the formation says, look, I'm the water, I'm here first, I'm going to say I'm staying, and I'm not allowing anything for hydrocarbon. The hydrocarbon obviously can migrate around this elsewhere in the reservoir, but at that depth there, that is non-net. So you can actually use a Pickett plot to calculate your RW above the free water level at these points, because these are fully water saturated. Does that answer your question?
Yeah, so you'd want to make sure that you cut those out before handing them over to the reservoir engineer, who may start panicking when he sees 100% water, at the top of a model.
The function, it can only be derived in the net reservoir sections. In the net reservoir sections, it's 100%. If your porosity goes even lower, it's still 100%. So you've definitely got to you have to calculate your net cutoff first of all, which is very easy to calculate, and then you apply that to your cross plot before you put the BVW function on. And just to say, I'm happy to receive plots of BVW, and obviously you disguise any sensitive information, and I will comment on it, because lots of people send me BVW functions, but they've included the non-net data, where water saturation, if it could be calculated, would be greater than 1. So that is very important. Yes, the net cutoff is important for the BVW function, and it is critical for the reservoir modeler.
Brilliant. Thanks, Steve.
Thank you, Steve. And probably last question over to Jan Lutgard. Or last 2 questions I think you have there, but let's see how they go.
Yeah,
Thanks.
let's start with the first one. Hi, Steve. Thank you for an interesting presentation, very interesting presentation. I love it when I see big scatter plots collapsing into almost straight lines. That's a really promising conversion that I hope will help us to solve many complex problems. My question is basically a Petrophysics 101. When we teach our students petrophysics, one of the first things that we show them is that grain size and porosity are basically independent. If you have perfectly round spheres with large porosity, so large spheres with large pores in between them, and we compare them with smaller spheres, also perfect spheres, you can show that porosity is exactly the same. So I was wondering if you apply this function at, let's say, a coarse grain, well-rounded coarse grain sandstone at a particular height above the contact, and you compare it with a siltstone at the same height above the contact, and we know that capillarity dictates that the siltstone has a much higher water saturation, then how would that play out using your approach?
Yes, when you go and look at the outcrops, you see that the nature of the rock reservoir varies considerably over a few feet. From the porosity, the shapes of the grains, the sorting, that. And so you think, how can you possibly have a reservoir model where it varies so greatly? Well, it varies a lot, but it's fractal in nature. This may indicate that the sorting for the very small grains is the same mathematically in 3 dimensions as for the large grains. we're still working on that, but it is fractal, and it's been shown to be fractal from many studies. So it's irrespective of the shape of the grains. Now, if you've got the shape of the grains in your database, put that on your z-axis as a color. So plot water saturation against height. You'll see that the grains give you a different water saturation. It separates out. Then move to BBW, do the data, and then drop onto a single curve, single exponential, or a straight line log space, irrespective of the shape of the grains or the size of the grains. And in many studies, we've seen that. But you can prove that yourself using that powerful tool, the crossplot.
Okay, okay. Am I allowed for a second question?
Yeah, go for it, Jan.
Okay, thank you. I also was wondering, when you have something in your reservoir that has an impact on saturation, and I was thinking on diagenetic clays, things like illite and smectites, that have a large impact on saturation, but not on porosity. So what would they, in theory, do with your relationship?
Yes, when you've got different minerals in the formation, so you've got pyrite, that will affect your resistivity log, but most reservoirs have some conductive shales in. So this really throws out your resistivity log. And we get around this by calculating the BBW function in the center of thick, clean beds. Remember, we only need one good point or 2 points to define the line. And then you apply that throughout. You apply it where you've got zones which have got different minerals and different shaliness. And you believe the function rather than the resistivity log, because the resistivity log is providing information to calculate the curve, but it is wrong close to these boundaries of where you've got a mixtures. Now, you said, well, how can we believe the function over the resistivity log? Well, we use the core data. We get quality core water saturations, and we said this is correct, but we only got that in a few wells and a few parts of wells. We compare the core water saturations with the function and resistivity log, and we show that we can ignore where the resistivity log is adversely affected by using only the best data, presuming that you've got something best which are clean.
Okay, so there's an important message here for management as well, that having core data available is critical.
Core data is very important, yes. Yes.
Okay.
But yeah, you can't get core data in all the wells, and where you've got it, that's where you check your function. The function from the core data could be exactly the same as from the log, and therefore they QC each other.
Okay. Okay. Thank you very much, Steve.
And what a wonderful message to leave it on there, Steve. Thank you very much. On behalf of all the audience, honestly, it was a fantastic presentation. So thank you very much for that. Really great. And we'll be posting it shortly on our LinkedIn and on our website, and posting it on LinkedIn. In 2 weeks' time, we'll be back with another classic saturation height function presentation with Dan O'Meara, and he'll be talking about pitfalls of 3D saturation modeling in Middle Eastern reservoirs. So I think the two talks go so well together, and look forward to most of you joining us again in 2 weeks' time. So with that, thanks again, Steve. Thank you very much. Really great presentation.
Thank you.
Thank you. Thanks to everybody. Bye-bye.
Thank you.